Okay, this next section of the Network Plus series is going to cover TCP IP addressing, and I'm going to do this in 3 Nugget movies, Part 1, Part 2, and Part 3. In this first part, we're going to be looking at a revisitation of the concept of MAC addressing, and we'll look at it in the context of TCP IP addressing. We'll also look at the IP version 4 addresses, addressing, and schemes, including touching on the concept of subnetting. But before we dive in, let me just tell you that we've already done a couple of nuggets in this series, and this was a challenge for me because when you take on a topic as broad and as complex as networking, you have to decide where you're going to begin, because some of the people that are watching your nugget, some of the learners may be just starting from scratch. I mean, do you start with the physical connectivity with the actual plugging in of the cables? Do you look at physical topologies? Do you look at logical topologies, like with the routers and switches and those types of things? Do you start out looking at things like network services and ports, which, by the way, is exactly where I began in this Network Plus series, network services and their ports? Or do you begin with applications? Applications like email, instant messaging, the World Wide Web? Or do you start with IP addressing? That's the challenge. Let me tell you the approach I'm taking and why. I'm basically going from top to bottom through the Network Plus exam objectives. I'm starting in the first domain, network technologies, then going to domain 2, media and topologies, then devices, then network management, then network tools, finishing up with network security, all the way down the line through the domains, looking at all of the objectives in order. The reason why I'm deciding to do this is this way I can guarantee that I get proper coverage of the Network Plus exam. What that means, however, is that I have to introduce technologies and terminology and concepts early on that I may be and will be explaining in greater detail later on in the Nugget series. So that's why it's very important for you to plan on going through this entire Network Plus Nugget series twice in its entirety, especially if you're new to networking. Well, with that being said, let's dive right into our first topic of Part 1, MAC addressing. Now, in the previous couple of nuggets, we talked a lot about port numbers, and everything has to have some type of address. And when we look at the services and applications that networks use, well, they're going to use things like port numbers, TCP and UDP port numbers, to create their sessions and their connections and their communications. Well, we need to have some type of address down at the physical and data link layers. So that's where our MAC address comes into play. Now, as far as computers are concerned, they're happy to use binary, zeros and ones. As a matter of fact, they're happy to represent things like network interfaces and switch ports as a binary number, zeros and ones. But for us human beings, it kind of helps to have maybe something like a hexadecimal address, which makes more sense. Now, do you have to understand how to do binary to hexadecimal conversion for this exam? No. And you can do it on a calculator very easily. What we have to understand is, first of all, and we talked about this earlier with the address resolution protocol, which we know maps this MAC address for a network interface card or the network interface on a port or a router. You can see layer 2, these frames. This mapping is done to an IP address. Now, the IP address, which we're going to see in a little bit, is a logical address. And it's not a unique identifier, okay? You can have hundreds or thousands of nodes all over the world using the same IP address. As a matter of fact, I can tell you right now that with all of the DSL routers and cable routers out there, there are literally thousands and thousands of hosts sitting behind those DSL routers using an IP address of 192.168.1.0 or something in that range. But MAC addresses, the media access control address, is considered pseudo-unique, okay, or quasi-unique. Should it be a unique identifier throughout all of the interfaces in the world? Well, yes, it should. That was the plan. But there are tools out there and there are techniques, and as a matter of fact, it happens even from particular vendors where you'll actually have network adapters with the same MAC address. Now, that doesn't really matter to us as long as that MAC address is not existing on the same network. We don't have a problem with it, but it is considered to be pseudo-unique. Okay, so the majority of network adapters have a unique 48-bit MAC address, and it's expressed here very commonly in kind of 6 groups where you have 3 bytes here and 3 bytes here, or 24 bits and 24 bits. Now what you need to know about this MAC address is this first 24 bits, or the first 3 bytes, are known as the OUI. Okay? That is the organizationally unique identifier. So we look at this diagram down here, we would see that all of these devices begin with 00. All right? Some of these are 0003, some of these are 0002. But it's the vendor that is assigned this first 24 bits, or the first 3 bytes. Then the vendor burns into the card, the network interface card that would go either connected to a port inside of the PC, or maybe it's integrated into the actual motherboard, or it's integrated into the laptop or whatever network device, or it could be a port on a switch. But these are basically doled out by the vendor or the manufacturer. 3Com, Cisco, there's a bunch of them. These are typically called BIAs, or burned in addresses, and because they're quote burned in, then they are supposedly going to be globally unique, even though that's not the case. As I've mentioned, there's actually programs out there, little hacker tools that we can get, that will actually modify the MAC address, and these are used actually in certain types of network attacks. Memorizing these particular addresses isn't important, but we do want to realize this, that there is a broadcast address, which means it's going to be received by all the stations on a local area network. So all the data link or layer 2 frames that get a broadcast would be FF:FF. Well, it's all F's. So let me just jot that down out there. When will we see this broadcast address? Well, for example, with the address resolution protocol. Okay, if a particular workstation here has an IP address of, let's say, 192.168.100.1 configured initially as this is the address to your default gateway, for example. If I don't have the mapping to this IP address, I'm going to have to broadcast on all F's to all of the stations on my network to find out, hey, who is the default gateway? So whoever has this particular IP address here is going to answer back to me in a unicast packet and say, well, hey, I'm the default gateway. I have this IP address, and now you know, and now you can add this to your ARP cache. So the address resolution protocol cache, as we know, has mappings of the data link layer 2 address, the physical address, to the logical internet address. So now that we have the MAC address part out of the way, let's now move to the IP version 4 address. And by the way, that's what we're looking at here on the left-hand side with the 192.168. Those are IP version 4 addresses. We're going to start there, and then we'll move on to IP version 6. Now, before we break down the granularities of the IP version 4 address, let's look at how these addresses are used. And again, this is very similar to what I talked about earlier with the FedEx packet and its header. Think about a letter being sent to the U.S. Postal Service, having some type of addressing. We need these addresses to get information, packets, or envelopes of data from one node to the other. So what happens here, again, here's our addressing or our mapping for, we'll call this host A over here, and we'll say host A sending traffic to host B. We've got a layer 2 to layer 3 mapping on this particular host. Here's the actual physical MAC address. Here's our logical IP address. Over here we've got on B the physical to logical mapping of the MAC address to the layer 3 address. And here's what's happening. Let's say I'm going to send an email message, which is the application data, by the way. And this email message that goes from this host to this host is going to start out as an email message. And then the software on this workstation is going to say, you know what, I'm TCP IP software. I'm going to use TCP IP, and this is actually going to be a TCP connection oriented. So maybe I'm going to start out creating the first three-way handshake, or maybe the three-way handshake's already been established, and I'm going to send the first part of the actual email message. I'm going to add to that particular application data a TCP header with all the information that's stored there. And then the TCP header is going to pass this down, and the application and the TCP header, which is now the data, is going to append some IP information to it, layer 3. So here's layer 5 through 7, session, presentation, application layer. Here's layer 4, here's layer 3, and again we start to add the logical addressing on here. The destination address 3.2, which is over here, and the source address, which is 3.1, which is here. Now this becomes the data packet and gets passed down. This is called encapsulation, and this gets passed down to layer 2, the data link layer, which of course this all becomes data, and appended to that is what we call a frame, where we have, well, we're going to say the source MAC address we know is 2222, and the destination MAC address is 1111. Now if these two hosts are on the same network, okay, this destination and source MAC address will stay the same in this particular communication, as will the IP address. However, if this particular information is actually moving through a router, for example, okay, it needs to be routed from one network to another, then actually this information, the MAC address information, is going to be modified, okay, because obviously this is going to be our default gateway, and what this destination MAC address is going to become is actually the destination MAC address of the default gateway. And of course the router gets this information. It's going to keep the source and IP address the same. That's the logical addressing, but the physical MAC addressing will be modified to its outgoing physical interface and the ingoing physical interface here. So the MAC address, the physical address, will change as it moves across in the network, but the source address, IP, and destination IP address, that is going to stay the same. Now there are exceptions to that rule when we talk about network address translation and port address translation, but it's important to understand how these addresses work. Now one of the first things you have to memorize is this particular table, so you're probably going to want to write this down on your own. And remember, from the standpoint of the machine or the computer, it's really dealing with just really a bunch of zeros and ones, or a string of 32 zeros and ones. But what we do is we take those zeros and ones and we break them up into 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to put dots here. We're going to break these up into 4 octets. Make sure I have the right number of bits here. Okay, so the first thing that happens is this string of zeros and ones gets broken up by 3 decimal points. So we have 4 octets, okay? And then we're going to translate this into a dotted decimal address of some type. So we're going to convert this into a decimal number. Now, it just so happens that with all the ones turned on, this would translate to 255.255.255.255. So what we have to understand first of all is, on a octet by octet basis, we have to memorize these 8-bit positions, the powers of 2, and the decimal values that are represented. So in first position, or if you turn that bit on, it has a value of 1. If you go to the second position with 2 to the first power and you turn that bit on, it has a value of 2, and so on. You can see we're just doubling here. So if we get to the 8th position, or 2 to the 7th power, if you turn that bit on, or the highest order bit, it has a value of 128. Now, notice how I mentioned that all these bits turned on is 255? How did I get that number? Well, if you turn on this bit, and you make this from 0 to 1 and 0 to 1 till you have all ones, if you do the math here, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals, you guessed it, 255. And so if you just change this lower order bit here from 1 to 0, that would equal, well, 254, right? If you turned this one into 0 as well, and you had 11111100, well, that's going to be 252. If I went ahead and said, you know what, let's turn this bit back on and make this one 1, okay, well, that's going to be 253. So that's how we come up with the decimal value that's represented by these 4 octets or the quads. And knowing these 8-bit values, you got to memorize that table. So remember, computers or machines, they're happy with zeros and ones. Applications, they like to have decimal numbers. But people, we like to have words. So that's why we go even further from this dotted decimal IP address to things like, well, host names and domain names. But that being said, one of the first things you have to learn is how to translate this octet and the bit values, the binary values, into a decimal value. So you can see here, I'll give you the first example. We're turning on the first 2 bits, which means we're going to be turning on, this has a value of 128. This has a value of 64. These are all turned off. So if you come onto your table here, you're turning on the first bit and the second bit, and 128 plus 64 equals 192. So obviously this first octet has a value of 192. Then we want to go ahead and just translate the rest of these. Let's go ahead and go to another slide to do that. But again, you can see how, first of all, we've got to have this set of numbers memorized. As a matter of fact, when I take an exam, a networking exam that involves any type of IP addressing or subnetting, I'll take the pad that they give me or the whiteboard that they give me, and one of the first things I do is I write down a table just like this. At least this row right here, I write down the 8 values of the octet. Okay, so we've already done the first octet here. We know that we turned on the 128-bit and the 64 bits. We've turned those on, the rest are off. We know that's 192. In this next one, we're going to turn on the 128-bit, we're going to turn on the 64-bit, we're going to leave the 32-bit off, turn on the 16-bit and the 8-bit, leave off the 4-bit, turn on the 2-bit. What we get is 128 plus 64 plus 16 plus 8 plus 2. That gives us a value of 218. The third one here, the third octet, we're going to turn on the 128-bit, turn on the 16-bit, turn on the 8-bit and the 4-bit and the 1-bit. That gives us 157. This one's easy down here. We're just turning on the 1-bit and the 2-bit. That's 3. So we can see our IP address is going to be now 192 for the first, 218 for the second, .157 for the third, .3. Now, if you can test that out if you want to. You could bring up a calculator here and say, well, let's just do this 157 one here. Okay, I'll go to binary mode and say, let's just look at this right down here. The first bit is on, that's 1. 64-bit off, 32-bit off, 16-bit on, 8-bit on, 4-bit on, the 2-bit off, the 1-bit on. And that looks a lot like what we're seeing down here. It's in binary. Just go to decimal, and there it is, 157. You can't use your calculator on the exam, but you can verify it with the calculator. Now, that's the easy part, really. I mean, once you start to get the feel for this, it's pretty easy. The hard thing is going the other way, okay? Saying, I've got 192.218.157.3. What if I have to convert that into binary? Well, that gets a little bit tougher. Let's take a look at that. Let's do the decimal number 157, okay? And of course, here's our 8 bits. We've got them turned. Here's the low order bit. Here's our 8 bits. Now we've kind of got them going vertically in a table. And we're going to start with the high order bit of 128. We ask ourselves, does 128 go into 157? Okay, yes it does. And it's only going to go into it once, of course. So 128 goes into 157. Turn it on 1 time. That leaves a remainder of 29. Okay, so we turn this bit on. Then we go, the next bit, 64. Does 64 go into 29? No, it doesn't. It doesn't go into it all. It goes into zeros times, so it still leaves a remainder of 29. Go to the next bit. Does 32 go into 29? Nope. So 32 goes into 29 0 times, still leaving us a remainder of 29. How about 16? 16 goes into 29 one time, so we're going to turn that on. 29 minus 16 leaves us 13, our remainder of 13. Does 8 go into 13? Yes, 8 goes into 13 one time, leaving a remainder of 13 minus 8, or 5. 4. Does 4 go into 5? Sure does. Goes into 5 one time, leaving a remainder of 1. Does 2 go into 1? No. 2 goes into 1 0 times, leaving a remainder of 1. Does 1 go into 1? It sure does. Turn that on. That's how we get 1 0 0 1 1 1 0 1. Now, if you can do this enough times to be able to do this in your head, then you're going to be in a lot better shape. But that's why it's so important to be able to memorize these 8 values of these 8 bits of the octet. That's how we go the other way, converting our decimal number into the binary octet without a calculator. Now, that's great. Let's say this host down here has an IP address of 192.218.157.3, which is the IP address that we just actually worked with. Here's the problem. So far, we have a 32-bit IP address assigned to this particular computer. But at this point, the computer doesn't know a critical question. This computer needs to know, what network am I on? It needs to know, of those 32 bits, of those 32 zeros and ones, which of the first bits represents the network, and which of the bits represent the actual host number on that network. In other words, it's fine to say Michael Shannon lives in Dallas, Texas. Okay? Dallas, Texas kind of says, this is the network I'm on. But what you really need to know to deliver that letter is, what is my street address? Okay? What is my particular home host identifier in Dallas, Texas, or the Dallas, Texas network? So we have to say, some of those first bits of those 32 are going to represent the network, and the remaining bits are going to represent the host. Now, it just so happens that what we do to do that, the mechanism we use, is called a subnet mask. In other words, we're going to use a masking or an ANDing technique, a mathematical ANDing process, to say we're going to tell you what subnetwork you're on. Now, it just so happens that we do this in the mask by turning the bits on. And this particular 192, as we'll see here coming up, traditionally is what we call a Class C IP address, which means the first 24 bits are the network address. So to turn on the first 24, if I turned on all 8 bits of this octet, we know that's 255. We've already established that. If I turn on all 8 bits of this second octet, we know that's 255. All 8 bits of the third octet, that's 255. We'll leave the last 8 bits to represent the actual hosts. So this is network right here. If we use this particular mask here, we're saying this is network 192.218.157. And of course, what dot 0 here? That's the network. This happens to be host number 3, or dot 3, on that network. As a matter of fact, this router address right here, this router interface, this is my default gateway. So this has to have an address on that network, and chances are it's going to be 192.218.157, running out of room here, .1. Typically the router interface, or the default gateway, a lot of times gets the first available address on that network. We can't assign it 0 because 0 is the actual network address. And this subnet mask of 255.255.255.0 says the first 24 bits are the network address, and the remaining 8 bits are the host address. Let me get my eraser out here. We can also represent this address like so. 192.218.157.3 /24. This is called a CIDR or a CIDR address, and this will make more sense later on. CIDR. The /24 simply says the first 24 bits represent the network. So we've got 32 bits, so 32 minus 24 leaves 8. So we've got 24 bits for the network portion. The last 8 bits are for the host. Now, if we've got 8 bits available for the host, we know that that 8 bits is going to be 2 to the 8th power. We saw that earlier on that table I gave you. 2 to the 8th power equals 256. So there's 256 combinations in this last octet. The problem is we cannot use the first possible combination, because the first combination would be all 8 bits turned off, right? 0, 0, 0, 0, 0, 0, 0, 0. All of them turned off. We can't use all zeros because that is the network address, right? 192.218.157.0. We can't use that one. And we can't use all the bits turned on because that is what we call the broadcast or the directed broadcast address. That would be 192.218.157.255. We can't use that address because all of the hosts on this network, if they wanted to talk to each other, for example, with a DHCP broadcast, these hosts wanted to broadcast to find the DHCP server, they're going to say, hey, 192.218.157.255, that's a directed broadcast. Now, to be more accurate, they're going to use 255.255.255.255. But applications can do what are called directed broadcasts because they have knowledge of their particular network or subnetwork. That's the bottom line. So in other words, we can't use 0, we can't use .0, and we can't use .255. So that means we've got 2 to the 8th power minus 2 possibilities, which is 256 minus 2 equals 254. So on this network, 192.218.157, we have a possibility and a potential for 254 addresses. We can give one out here to the default gateway. This computer got one of them. We've got 252 left over for all of our workstations, our departmental servers, our printers, our laptops, whatever. Well, as you can start to see here, that limits us, and that limits this network or subnetwork to only 254 hosts. And you know what? There's a lot of networks out there that are bigger than 254 nodes. So we may need to use some other type of addressing scheme or subnet mask besides 255.255.255.0, because that gives us a whole bunch of networks, right? A bunch, trust me, but only 254 hosts per network. Now the next IPv4 mechanism we need to know about is that of what's called classes. And early on in the IP addressing scheme of TCP IP, the architects and designers decided to break up all 32 bits into 5 different classes. And they did this not really thinking that eventually this network, this research and development government / large corporations / university network would ever be taken over by the World Wide Web and things like YouTube. So without thinking, they broke up these networks into classes. The class A had a IP address range of the 1.0.0.0 through 126 network. Okay, these were the biggies. These were things like 3M and some of those early universities like Stanford and IBM and companies like, the big beginning internet players. So there was 126 networks, but there were 16 million hosts per network, and the default subnet mask for class A was 255.0.0.0, which meant the first 8 bits were being masked out for the network portion, and then you had 24 bits here for the host on each network. So that's a lot of hosts there. Then they broke them up into Class B. Class B was the next big group of people, like Microsoft, for example, got a Class B. Class B was the 128.0.0.0 through 191.255 network. and their subnet mask was 255.255, which meant the first 16 bits, or the first 2 octets, were set aside for the network, and then they had .0.0 for the host. And you can just see here, 65,534, well, 2 to the 16th power minus 2 just happens to equal 65,534. So we could have that many hosts per network. And again, here's our class C that we saw, 192.0.0.0 through 223, and that was with a default subnet mask of 255.255.255.0, and there was my 254 hosts per over 2 million networks. Now, there's something missing here. We went from 126 to 128. What happened to 127? Well, the designers set 127 aside, the 127 network, as a testing network, which was a bummer. And the loopback address, if you want to test your own system, this represents your system, 127.0.0.1. If you install the TCP IP stack or software on your computer, it knows that address 127.0.0.1 is the loopback address, and that's how you test your own system. For example, we talked about ping in the previous nugget. I could ping 127.0.0.1, and if it answered back, that would be basically telling me my computer has a functional TCP IP stack installed on it. Class D is the multicast. Multicasting is how we send to a group of computers, regardless of their location, their proximity, their geography. We can group up a bunch of computers, for example, for webcasting or for video streaming or for online gaming. We can group them up into a multicast group. D is for multicast, E is for experimental. We don't really care too much about these. By the way, routing protocols and other protocols also use multicast addresses as well, and we'll talk about that when we get to routing protocols. So this classful system with its default subnet masks worked fine in the beginning, but then eventually it became troublesome. For example, a lot of organizations, they just kept their Class B addresses, and we started running out of IP addresses. As countries like China and India and Brazil and countries in Africa started getting on the internet, we ran out of these IP version 4 addresses. Okay? It's a finite amount of addresses and not enough. So we had to come up with mechanisms to get around these rules. The first mechanism that we came up with to get around these rules was to use classless interdomain routing, CIDR, which meant we no longer have classes. No more Class A, no more Class B, no more Class C, and no more reliance on this default subnet mask. For example, we could take an address like the one we had earlier, 192.218.157.3, and instead of being stuck with 24 bits for the network and 8 bits for the host, or /24 is the cider way to do it, we could say, you know what, forget that. We'll just make it /16, which means the first 16 bits is the network, and the last 16 bits are the host. We now have, this looks like Class C, it smells like Class C, it feels like Class C, but it's not Class C. We're using classless now, so we now have 65,534 available on this, what used to be a Class C. And we can even get more clever with this. If this is just way too many hosts, we can say, you know what, let's just get clever and let's just change this from /16 to, oh, I don't know, how about /18 or /22. In other words, we'll vary the length of this subnet mask to give us just the right amount of hosts and just the right amount of networks that we need. So we use things called classless interdomain routing and variable length subnet masking to create what are called subnets, okay, or smaller networks of larger networks, and supernets. So we can combine a bunch of subnets into one supernet. And this is all done to improve routing and to improve our IP addressing infrastructure. So those mechanisms are in place, and they're very important. Now, the best way to understand how to do subnetting is to go up on the internet and get a subnet calculator. I'll just jot this down for you. Subnet calculator. And a subnet calculator is the best way to learn how to do subnetting, or in other words, modifying this CIDR prefix here from 16 to 17 to 22 to 23, vary the length of our subnet mask or our CIDR prefix to get just the right amount of hosts we want. Remember, the hosts are basically the bits to the right and the network are the bits to the left. Now, by the way, do you need to know this table for your exam? Yes, you do. Even though we don't really use this classful mechanism anymore, you still need to know the classful mechanism because it still affects us out there. Now, getting really clever with that CIDR prefix and creating subnets isn't as important anymore as it used to be because of the wide usage of what we call network address translation. Well, there you go. That's it for TCP IP Addressing Part 1. We looked at MAC addressing and the IP version 4 addressing structure and schemes. We're going to take up here where we left off in Part 2. We're going to look at addressing destinations. And this is things like unicast and multicast and broadcast and anycast. And then we'll go and explain IP version 6. I hope this CBT Nugget has been informative for you. I want to thank you for viewing. We'll see you in Part 2.